Um, when you look at a traditional medical diagnosis, I feel like the foundational assumption is always, well, structural breakage.
Right. Yeah, you expect to see something physically wrong.
Exactly. Like you fracture your tibia, you look at the radiograph, and the jagged fissures it's undeniable, right? The physical architecture of the system has visibly failed.
Yeah, the macroscopic intuition we have, it just makes sense to us.
Right. And we carry that intuition down into the microscopic world when we look at oncogenic mutations, these rogue proteins that drive human cancers. We inherently expect to find a physical deformation.
Mm-hmm. A warped binding pocket or like a broken structural hinge somewhere.
Yeah, exactly. But welcome to this deep dive, everyone. Today we're exploring a phenomena that honestly challenges the very foundation of molecular biology.
It really does. We're looking at allostery without conformational change.
Right. Which means we're unpacking how a protein can transmit this complex signal from one end of its structure to the other, or in the case of a cancer driver, lock itself into a hyperactive state without any globally discernible change in its actual physical shape.
Which is wild because it forces us to basically abandon that classical metaphor of proteins as these, macroscopic machines.
Yeah, like we can't think of them as simple assemblies of levers and gears anymore, right?
Exactly. It's not just a trapdoor that opens when you pull a string on the other side. It's much more subtle than that.
So to navigate this, we are diving into a landmark paper published by Fatma Singular-Shifchi, and for our listeners, that's pronounced Shifchi and Burak-Ehrman.
Oh, this paper is just phenomenal.
It is. It's titled Spanning Tree Thermostatistics of Protein Allostery, an exact Kirchhoff framework with application to oncogenic KRAS. And what Shifchi and Ehrman have done here is, it's just extraordinary.
Yeah, they didn't just build another structural model. They pulled in these incredibly rigorous concepts from algebraic graph theory.
Right, specifically things like spanning trees and cycle rank, which we'll get into.
And they integrated all of that with statistical mechanics to create this completely new thermostatistical framework.
And the mission for our deep dive today is to really unpack this. The audacity of their approach, I think, lies in mapping pure information flow.
Yes. They are quantifying the invisible thermodynamic communication networks inside a protein.
And the best part is they don't just leave it as abstract math. They deploy this framework to solve the mechanistic mystery of the KRAS G12D mutation.
Which is one of the most notoriously intractable cancer drivers in oncology.
Exactly. So they're mapping how a protein becomes a lethal signaling hub while wearing like a perfect physical disguise.
It's a total paradigm shift.
It really is. But before we dissect the specific topological rerouting in that KRAS mutant, we really have to establish the computational lineage here, right? Because science builds on its precedent.
Oh, absolutely. You can't appreciate the new framework without understanding what came before it.
Right. And to understand the gravity of this spanning tree thermostatistics, we need to trace the intellectual ancestry of the senior author, Burak-Ehrman.
Yeah, Ehrman's influence in this field is it's foundational.
So where does his trajectory really start?
Well, it traces back to his extensive work at Stanford, actually, with Paul Flory.
Oh, right. The polymer chemist. He won the Nobel Prize, in 1974?
Yep, 1974. And Flory's work fundamentally defined the statistical mechanics of chain molecules. He figured out how to mathematically model the spatial configurations of these long random coil polymers.
By treating them as statistical ensembles, right?
Right.
Rather than just static structures.
Exactly. And Ehrman took those profound insights into polymer elasticity and chain dynamics and adapted them to arguably the most complex polymers of all, which are folded proteins.
Which brings us to the late 1990s when he co-developed the Gaussian network model, or the GNM.
Yeah. And that model effectively birthed modern computational structural biology.
Okay, let's unpack this for the listener because the GNM is super important here. Prior to the GNM, our primary tool for visualizing protein dynamics was what? Molecular dynamics? MD simulations.
Right. And MD is notoriously computationally expensive. You were integrating Newton's equations of motion for tens of thousands of atoms.
In femtosecond time steps, yeah.
Yeah. You need massive supercomputing clusters for that. And even then, your simulation can easily get trapped in a local energy minimum.
Wow. So it was a massive shortcut.
It was a revelation. Virtually every modern elastic network model used today traces its architectural DNA right back to Ehrman's original GNM formulation.
Okay, but let me push back a little here. If the Gaussian network model is so foundational and everyone uses it, why do we need this new framework now? Why spanning tree thermostatistics?
Well, physics is nuanced, right?
Hmm.
And the classic GNM had this glaring thermodynamic blind spot in how it defined the topology of those mathematical springs.
Because it relied on a binary step function cutoff? Or...
Yes, exactly. You'd have to choose an arbitrary distance limit, let's say 7.3 angstroms.
Okay, so if two alpha carbons are 7.2 angstroms apart.
The matrix assigns them a spring constant of 1. They interact perfectly. But if they're 7.4 angstroms apart,
Just a tiny bit further.
the matrix assigns a 0. No interaction whatsoever. It just drops off a cliff.
And the physical reality of atomic interactions just completely rejects that binary logic.
Yeah, totally. The dominant forces holding a folded protein together, like van der Waals dispersion forces, electrostatic interactions, hydrogen bonding, they decay continuously.
They don't just snap to zero.
Right. They follow distance-dependent potential functions, like the Leonard-Jones potential, which, tapers off asymptotically.
So by using a hard step function, the old GNM treated the dense, tightly packed hydrophobic core of a protein identically to the really loose, solvent-exposed loops on the outside.
Exactly, provided those residues fell within that arbitrary cutoff sphere.
Which effectively flattens the whole energy landscape.
It does, and this is exactly the limitation that Sifji and Ehrman resolve with their new spanning tree thermostatistics, the STT framework.
So how does the STT evolve the GNM?
It completely discards the binary cutoffs. Instead, it assigns interaction weights using a continuous exponential decay function based on the actual physical distance between the residues.
And the mathematical consequence of that continuous decay has to be massive.
Oh, it is, because it inherently biases the network toward the high-density structural conduits.
The core residues.
Right. Because they're physically closer together, they receive exponentially larger interaction weights.
So the model basically organically differentiates between a super tenuous peripheral hydrogen bond and, the rigid architectural scaffolding of the protein core.
Yes. The STT captures this high-resolution heterogeneous map of the internal forces, and that is what allows it to define what the authors term topological microstates.
Okay, so to really grasp this concept of a topological microstate, we have to kind of transition from the language of physical chemistry into algebraic graph theory, don't we?
We do. The STT framework visualizes the protein backbone as a weighted graph.
So the amino acids, the alpha carbons, are the nodes, or the vertices.
And the physical forces connecting them, weighted by that continuous exponential decay we just talked about, those are the edges.
Okay, I like to think about this using the analogy of a city traffic grid.
Okay.
Because if you look at the complete protein graph, it is intensely dense. If there's only one road connecting point A to point B in a city, the system is super fragile. A single accident shuts down the whole city.
Right.
But a protein, thanks to evolution, has immense topological redundancy. It's got multiple overlapping cyclic routes, like a major metropolis.
That's a great way to put it. And in graph theory, that redundancy is quantified by something called the cycle rank.
Also known as the first Betty number in topology, right?
Yes. And practically speaking, the cycle rank is the exact count of independent cycles, or alternative pathways, in your city analogy, that exist beyond the absolute minimum required to keep the graph fully connected.
So a high cycle rank means high topological entropy.
Exactly. It means the allosteric communication network has a vast statistical ensemble of possible routes it can use.
So if a localized thermal fluctuation temporarily weakens one set of hydrogen bonds, the signal doesn't just die. It dynamically reroutes through the excess edges.
Right. Which brings us to the titular concept of the whole paper. The spanning tree.
Okay, yes. Define this for us.
So if the full protein graph represents all possible connections simultaneously, a spanning tree is a maximally reduced subgraph.
Meaning you systematically delete edges from the network.
Until you reach the precise point where every single node is still connected, but there are 0 cycles.
Zero redundancy.
Exactly. The cycle rank drops to absolute 0.
So in the STT framework, one single spanning tree equals one topological microstate.
Yes. It is an instantaneous snapshot of a single, unambiguous pathway connecting every residue in the protein.
So if you want to push a signal from a regulatory domain to an active site within that specific microstate, there is literally only one directed sequence of edges that the signal can take.
Precisely. But the thermodynamic power of this model comes from recognizing that the protein isn't static.
Right, it's constantly fluctuating through millions of these different microstates.
So the total allosteric capacity of the protein, the entire global signaling landscape, is defined by the sum of all its possible spanning trees, the complete statistical ensemble.
Okay, but wait. If a protein has hundreds of residues and thousands of interatomic contacts, the number of possible spanning trees has to scale factorially.
Oh, it's astronomically large. Millions, billions of potential trees.
So aren't we just guessing at that point? Like, how on earth do we calculate them all without a supercomputer crashing? The computational overhead would rival the MD simulations we're trying to avoid.
And that is exactly the computational bottleneck that has historically prevented researchers from mapping pure information flow. But, and this is the magic of the paper Sifchi and Ehrman, bypass it completely.
By invoking Gustav Kirchhoff's matrix tree theorem from 1847.
Yes, a theorem originally developed to analyze current flow in electrical circuits.
Okay, this is fascinating. How does it work for proteins?
Well, the authors construct something called the weighted Laplacian matrix of the protein.
Okay.
The diagonal elements of this matrix contain the total interaction weight for each node, essentially, its degree of connectivity.
And the off-diagonal elements.
They contain the negative interaction weights between any two connected nodes.
Got it. So we have this big Laplacian matrix.
Right. And by analyzing its algebraic structure, Kirchhoff's theorem provides this profound mathematical shortcut. If you take that Laplacian, remove any one row and its corresponding column to create a reduced matrix,
Okay.
and then you calculate the determinant of that reduced matrix, that single numerical value exactly equals the sum of the products of the edge weights for every possible spanning tree in the entire graph.
Wow. So the determinant just gives you the exact global partition function.
Exactly. There is zero stochastic sampling required. No Monte Carlo simulations.
Go guessing.
No guessing. You perform one linear algebra operation, and you capture the exact closed-form sum of the entire topological ensemble.
It's an exact mathematical snapshot of the global communication capability of the protein. That is so elegant.
It really is. But of course, that gives us the global state. The analysis eventually have to shift to local communication.
Right, because we need to know how two specific distant sites communicate. Like from an allosteric binding pocket all the way to the catalytic active site.
Yeah. And to achieve that kind of resolution, the SDT framework employs another mathematical tool, the Burton-Paymantle theorem.
Okay, here's where it gets really interesting for you listening. Because in electrical networks, the Burton-Paymantle theorem acts as a way to calculate transfer impedance.
Right. And in the STT framework, it basically acts as a mathematical zoom lens. It calculates the specific probability that a given local interaction edge is actively participating in the global allosteric flow.
And it does this by calculating the dynamic node-to-node distance, right?
Yes, and dynamic distance is very different from physical distance. It relies on something called the Moore-Penrose pseudo-inverse of the unreduced Laplacian matrix.
Which sounds incredibly complex, but essentially Euclidean distance just measures the physical space between two atoms in angstroms, right?
Right. But dynamic distance measures the functional topological resistance.
So if two residues are physically adjacent, like right next to each other in space, but they're separated by a rigid structural domain that has really low network connectivity,
their dynamic distance is actually massive. The signal cannot easily cross that divide.
But conversely, two residues separated by, say, 40 angstroms could have a tiny dynamic distance if they happen to be connected by a highly coordinated rigid conduit of core residues.
Exactly. It's about the highway, not the crowfly's distance.
So by extracting the variance of this dynamic distance across the entire ensemble, they can calculate the precise heat capacity and entropy of any single microscopic communication channel inside the protein.
Yes. They can quantify the exact thermodynamic flexibility of these invisible information pathways.
Okay, so the SDT framework is this incredible exact mathematical lens. Now, we need to prove that it actually works in biology.
And to do that, Sifchi and Ehrman applied it to one of the most notorious molecules in oncology, KRAS.
Specifically, the G12D mutation, which is just a major, major driver of human cancers.
Yeah. KRAS normally operates as a cellular signaling hub. It's part of the MAP-CARC pathway.
It's essentially a binary biological switch, right? When it's bound to GDP, it's inactive.
Right. And then guanine nucleotide exchange factors, or GEFs, swap that GDP for GDP. And that causes KRAS to undergo a conformational shift in two specific regions, known as switch I and switch II.
Which is the active state.
Yeah.
That recruits downstream effector proteins and initiates cellular proliferation and growth.
Exactly. And to turn that switch off, KRAS has to hydrolyze the GTP back into GDP.
So it acts as its own timer.
Yeah, it has intrinsic GTPase activity, which gets heavily accelerated by GAP proteins. But the G12D mutation.
This occurs at the 12th position of the amino acid sequence, directly in the P loop, which wraps around the phosphate groups of the GTP molecule.
Right. And the mutation swaps out a small, flexible glycine residue for a much larger, negatively charged aspartate.
And that one single substitution severely impairs both the intrinsic GTP hydrolysis and the ability of the GAPs to bind and help out.
Meaning the KRAS G12D protein becomes permanently trapped in the GTP-bound active conformation.
It's just signaling continues to grow.
Yes. Driving unchecked cellular division. It is a primary driver in pancreatic cancer, colorectal cancer, and non-small cell lung cancer.
It's lethal, but here is the massive biological mystery that we hinted at in the intro. When structural biologists crystallized the KRAS G12D mutant, which is documented under PDB-ID6GOF, and they superimposed it over the wild-type healthy KRAS protein.
PDB-ID6GOD, yeah.
Right, when they compared them, they found a structural paradox. The two proteins look essentially identical.
It's crazy. The root mean square deviation of their atomic coordinates is just a mere 0.19 angstroms.
119 angstroms, that's nothing. The G12D mutation does not induce any significant global conformational change.
The macroscopic machine hasn't worked at all, and the STT framework analysis actually deepens this paradox.
How so?
Well, when you evaluate the global thermodynamics using STT, the total internal energy, the global topological entropy, the global heat capacity, the values remain incredibly stable.
They don't change either.
Barely. The global metrics fluctuate by only about plus or minus 0.5% between the healthy version and the deadly mutant.
Wait, let me push back on this, because for the listener, this sounds impossible. If the mutant physically looks exactly like the healthy version, and its global thermodynamics are identical, how is it causing cancer? How did the protein even know it's mutated?
And that is the aha moment of this entire paper. The global numbers are a mirage. They are masking a massive internal rerouting of information.
The disruption is hidden within the variance of the partition function.
Exactly. And to uncover it, the authors deconstructed the specific heat capacity of individual signaling channels inside the protein.
Okay, this deconstruction is really the analytical core of the paper, so let's walk through it.
Sure. So the heat capacity of an allosteric channel is broken down into three constituent terms.
The first is the energetic component, right? C subscript E.
Right. CE day quantifies the variance in the physical interaction weights, so the localized flexibility of the chemical bonds forming that specific path.
Okay, and the second term is the topological component, C detal.
Yes. This measures the variance in the cycle rank of the surrounding network. Basically, how the global redundancy of the protein supports that specific channel.
Got it. So we have local energy and global topology. What's the third term?
The third is the cross-coupling component, C-Scheik-Zollars. This is the covariance term. It measures the dynamic correlation between the local energetic fluctuations of the channel and the global topological fluctuations of the protein matrix.
Okay, so when they actually analyze these vital signaling channels in the KRAS mutant, what did Sifchi and Ehrman see?
They observed violent shifts in the CE and C-Guy-Sardollar terms.
Massive spikes.
Huge. The local physical strain increased massively, and the immediate topological support structure was highly disrupted by that bulky aspartate.
But the protein didn't break.
No, because they discovered that these massive local deviations were perfectly offset by equally massive negative shifts in the cross-coupling C-Scheik-Zar term.
They call this the compensation principle.
Yes. The background protein matrix operates as a thermodynamic shock absorber.
It's like, okay, going back to my city analogy, imagine a major highway bridge suddenly collapsing.
Okay.
The total amount of traffic in the city, the global number of cars, stays exactly the same. The city doesn't disappear.
Right. The global metrics are stable.
But the side streets are suddenly chaotic. Everyone detours. The network doesn't break, it just heavily reroutes the traffic to absorb the strain.
That is a perfect analogy. The cross-coupling term absorbs the energy. Consequently, the total heat capacity of the channel appears conserved, totally masking the internal chaos. The physical architecture maintains its integrity by sacrificing its internal signaling pathways.
The routes are entirely rewritten.
Yes. And to visualize this rerouting, the framework utilizes something called the Jensen-Shannon divergence.
Right, which is an information theory metric that quantifies the difference between two probability distributions.
Exactly. And by calculating the Jensen-Shannon divergence between the wild type and the mutant spanning tree ensembles, we can see exactly how the allosteric importance of individual residues shifts.
And the data from the paper reveals a dramatic redistribution of the signaling load. Let's dive deep into the specific residue data here, because this is where the pathology becomes clear.
Well, we can trace it directly. In the normal KRAS protein, glycine 12 acts as a central node in the allosteric network.
But in the mutant, it's an aspartate.
Right. And that bulky side chain sterically hinders the optimal pathways.
So the Jensen-Shannon divergence shows the allosteric importance of position 12 plummets.
Yes, by nearly 25.9% in the channels leading to the switch 2 region.
So the mutation physically barricades its own pathway. It abandons G12.
Exactly. And with the primary conduit blocked, the network topology forces the signal to seek an alternative route.
The detour.
The detour. The thermodynamic pressure reroutes the allosteric traffic right into glutamine 61, Q61.
And the data shows its allosteric centrality spikes, right, by almost 22.7%.
And the physiological consequence of this specific rerouting is devastating.
Because in a functional KRAS molecule, Q61 is a critical catalytic residue, isn't it?
Yes, its primary function is to position and polarize a catalytic water molecule. That water molecule facilitates the nucleophilic attack on the GTP to cut it.
It is the literal mechanism that turns the switch off.
Right. But the STT framework shows that the G12D mutation effectively hijacks Q61.
By forcing massive allosteric traffic through it.
Exactly. It repurposes Q61 from a localized catalytic worker into this global communication hub.
It gets distracted from its actual job.
Yes. It becomes dynamically constrained by the signaling load. It can no longer optimally orient that catalytic water molecule.
Which drastically lowers the rate of GTP hydrolysis.
And that structural hack traps the KRAS protein in a permanently on-cancerous state.
Wow. And the structural data never captured this because Q61 hasn't physically moved.
Right. It hasn't moved a significant distance. Its dynamic assignment within the topological ensemble is what changed. The internal job description was rewritten by the shifted thermodynamic weights.
But the topological rerouting doesn't end at the active site, does it?
No, it doesn't. The STT analysis reveals that the most severe perturbation in the entire network occurs far away from the mutation.
At the far end of the protein.
Yes. The signal traffic surges toward phenylalanine 156, F156.
And the allosteric importance of F156 increases by an astounding 35.5%.
It's the most massive shift in the whole network.
So what does F156 normally do?
Well, KRAS is essentially composed of two lobes. An effector lobe that binds downstream targets, and an allosteric lobe that regulates membrane orientation. F156 acts as the structural hinge between them.
Okay, so it's supposed to be flexible.
Exactly. But this massive influx of topological traffic forces F156 to rigidify. It transforms from a flexible hinge into a highly constrained, rigid bottleneck.
Which dynamically locks the relative orientation of the two lobes.
Right, further stabilizing the hyperactive state of the entire molecule.
So the cancer driver mechanism is entirely allosteric. It's a long-range transmission of thermodynamic strain.
Yep.
But this raises a fundamental question of mechanism for me. Without a centralized intelligence guiding it, how does a fluctuating protein network predictably choose to route the blocked signal, specifically through Q61 and F156, rather than just dissipating it randomly through the hundreds of other available residues?
That is a great question. And the routing is governed by something called the principle of minimum surprisal.
Which derives from Shannon entropy, right? Information theory.
Exactly. In statistical mechanics, any physical system will naturally seek a state of equilibrium that minimizes its free energy. In information theory, a network will route information along the path that minimizes surprisal.
Essentially the path of least resistance.
Right. Surprisal, in this context, is the negative logarithm of the probability of a specific pathway.
So a path with high surprisal requires a really highly improbable configuration of microstates to actually happen.
Exactly. While a path with low surprisal relies on stable energetics and dense network topology.
Okay, so the G12D mutation alters the local energetic weights around the active site.
Yes, which massively increases the surprisal of the wild-type pathway through residue 12.
Normal road is closed, high surprisal.
So the network must re-equilibrate. And due to the existing pre-wired geometry of the KRAS molecule, the specific channels passing through Q61 and F156 possess the requisite topological redundancy to absorb that displaced signal.
Following the laws of thermodynamics, they become the new paths of minimum surprisal.
Yes. The mutation doesn't actively target Q61, it just alters the global topographical map, and the information flows downhill into the newly established topological valleys.
That is incredible. And this mathematical determinism has to have profound implications for pharmacology, right? So what does this all mean for the listener who wants to know how we cure this?
Well, historically, discovering small molecule inhibitors for KRAS has been incredibly frustrating.
Because the mutant structure is nearly identical to the wild type.
Right. So traditional drugs try to target the active site or the mutation directly. But because the shapes are conserved, attempts to design competitive inhibitors often result in drugs that inhibit healthy KRAS in normal cells, too.
Which leads to severe systemic toxicity.
Mhm.
We can't distinguish the broken machine from the healthy one.
Exactly. But the spanning tree thermostatistics framework provides a completely novel targeting paradigm. We no longer need to target the mutation directly.
Because we can target the detour.
Yes. The survival of the oncogenic state relies absolutely on these newly formed, low-surprisal allosteric highways. The cancer is dependent on the F156 bottleneck to maintain that hyperactive interlobe orientation.
So drug designers can build molecules to target these hidden bottlenecks. If you build a drug to specifically bind near the F156 or A155 residues at the interlobe bridge,
You wouldn't need to physically alter the active site at all. You would simply increase the local energetic strain at that bottleneck.
you artificially increase the surprisal of the pathological pathway.
Exactly. The topological resistance becomes too high, and the signaling network is thermodynamically forced to reroute again,
Disrupting the internal communication hack.
potentially restoring the flexibility of the catalytic Q61 residue and re-enabling GTP hydrolysis, all without ever touching the G12D mutation itself.
That is absolutely mind-blowing. We are looking at the foundational logic for allosteric drug design, driven entirely by exact mathematical topology.
It really is the future.
So, to summarize the journey we've been on today, we have tracked the evolution from Paul Flory's random coils through Burek-Ehrman's foundational Gaussian network model.
And arrived at the standing tree thermostatistics framework.
Right, a framework that discards the physical limitations of those old binary cutoffs, utilizing continuous exponential decay to accurately map the structural density of the protein core.
By mapping the protein as a network of nodes and edges, defining redundancy through cycle rank.
And using Kirchhoff's matrix tree theorem to calculate the exact global partition function of all possible spanning trees, Schiffchi and Ehrman achieved an analytical solution to protein allostery.
And by applying the Burton-Pimentel theorem and the Moore-Penrose pseudo-inverse, they established the dynamic node-to-node distance, which proved the compensation principle.
Showing us exactly how cross-coupling buffers the global thermodynamic changes, even while the internal signaling routes are vastly altered.
Which is what allowed them to unmask the silent lethality of KRAS G12D.
Right, the mutation physically barricades its own node, forces the information flow along the paths of minimum surprisal,
Hijacks the catalytic Q61, trapping the protein in the active state.
and surges into the F156 interlobe hinge, rigidifying the entire molecular architecture. The implications of this extend so far beyond oncology.
They do. I want to leave you with a final thought to mull over. We've spent a century viewing diseases as physical breakages, like a gear snapping in a machine. But this framework suggests we should view disease as an information problem. A cancer cell isn't necessarily a broken machine. It's a machine where the internal communications have been perfectly, elegantly hacked.
The underlying pathology is not physical deformation. It is a topological hack of the information flow.
Exactly. And if we can map the hack, we can rewrite the code.
By translating the complex physical chemistry of a protein into the exact analytical language of algebraic graph theory, we finally have the tools to do just that. Thank you so much for taking the plunge with us today. Keep questioning the invisible networks underlying the macroscopic world all around you, and we will catch you on the next deep dive.